Good day, my dear people. I'm here to present a lecture on moment area methods for obtaining deflection. In many analytical methods of structural analysis, this method is very handy in obtaining the deflections and making analysis simpler. This lecture note is presented by Chief Ous M. Ibarublem Ugom Sinachi 1 of Umezegu, B. Engine Civil Engineering, M. Engine Structural Engineering, PhD Structural Engineering. He is a reader of Civil Engineering, Federal University of Technology, Owerri. This note was prepared for my students in the Department of Civil Engineering, those at 400 level, doing their Structural Analysis 1. The first thing to be done is to determine the strength energy of the element. Strength energy is a form of potential energy defined as the product of loads and deformation, as you can see on equation 1, U representing strength energy, P representing load, and delta representing deformation. If you differentiate this equation with respect to deformation and do rearrangement, you will get element strength energy equation for the beam, as you can see on equation 2. du equals P d delta. Hooke's law will also be applied here, where it is said that applied load is directly proportional to deformation. This is evident on equation 3. Another law is that of Young modulus, which says that stress is directly proportional to strain, as you can see on equation 4, where K and E are spring constants and Young modulus of elasticity respectively. Stress is a ratio of applied load to area of cross section. This is seen on equation 5. You can see dividing the applied loads with the cross-sectional area of the member, or the area of contact or area receiving the loads, you will get stress. You can see it here. Sigma represents stress equals P represents load all over A, which represents cross-sectional area of the member. Another mechanical property we are introducing is the strain. And strain is the ratio of deformation to the original length of the member. This is evident on equation 6, where epsilon equals delta, that is the deformation, divided by L, which is the original length. Substituting this equation 5 into equation 6, substituting equations 5 and 6 into equation 4 gives what you have on equation 7. That is load over area equals Young modulus times delta all over L. Upon rearranging equation 7, we will get an equation for loads, which is Young modulus times cross-sectional area divided by the original length times the deformation. That is what you are seeing on equation number 8. Differentiating equation 8 with respect to deformation and rearranging the resulting equation gives the elemental deformation equation, as you can see on equation number 9, as this. Substituting this equation 9 into our earlier equation number 2 will give us this equation 10. That is the latest definition for elemental strength energy of the elements. Just what you need to do is substitute this equation number 9 back into our equation 2, and definitely you are going to get this equation number 10. You are going to use this equation later. Note it, it's very, very important. Integrating that equation 10 in the domain of initial loads and final loads and do some rearrangements, you will get the equation for total strength energy as presented on equation 11, where P1 is the final value of the load which starts from rest. That is, initial applied load is 0, that starts from rest, to the final value of the load, which is P1. So equation 11 is our total strength energy equation. At this very point, we have obtained our basic equations. The next stage is to move into the Castigliano's first energy theorem. This theorem states that displacement is the partial derivative of total strength energy with respect to applied loads. That is, when you differentiate the total strength energy partially with respect to the applied load, you are going to get displacement, in this case deformation. That is what is called Castigliano's first energy theorem. This Castigliano's first energy theory is an important theory in structural mechanics. You will see later that the outcome of this theory will help us determine the values of displacement at any point arbitrarily selected along the beam. It's going to be fun as we progress. So you can see equation 12. That is the ratio, or I can say the first derivative of strength energy with respect to P. Or I can say partial derivative or partial differentiation of strength energy with respect to applied loads will give us the deformation delta. This is stated on equation 12. Substituting equation 11 into equation 12 and doing some mathematical readjustments, you will arrive at equation 13, which is the formula we are going to use to determine the deformation at any point on any truss member, assuming you are doing truss analysis for statically determinate trusses. This equation 13 is very veritable and handy to be used. But in the course of this course, we are dealing on beams or frames, as the case maybe, that's flexural frames. So in this case, we are dealing with flexural members. We are going to replace the loads instead of P to be moment, then the cross-sectional area to be second moment of inertia. So if we do that, equation 13 will now become exactly what happened on equation 14. Whereas equation 13 can be used for truss members, equation 14 is used to analyze beams and flexural frames. In this case, we are dealing with moments, not direct forces. The length of the member or the beam, as the case may be, is L, and it is defined as integral of the x, whereas x is the infinitesimal distance at any arbitrary point along the beam. When you integrate this dx from the beginning of the beam to the end of the beam, you get the total length of the beam represented on equation 15. Substituting equation 15 into equation 14 gives the formula presented on equation 16. We can isolate or factorize the m1 dp out of the integral bracket as shown on equation 17. So at this equation 17, you will notice that the one out of the bracket can be treated as a constant, and the term inside the integral bracket treated as variable. That is the displacement at any arbitrary point on a loaded beam shown on equation 17. Equation 17 can be interpreted as follows. Deflection is the product of moment area and ordinate of moment due to unit loads. That is, the term outside the integral bracket is the ordinate of moment due to unit load, and the integral is the moment area. Look at what you have. You will see a beam loaded with uniformly distributed loads and 3-point loads. After analyzing the beam and drawing the bending moment diagram, we shall have the area of that moment diagram represented as the integral of m over ei dx. That is this. So this is the area of this parabola we are seeing here. Then on the other way, the beam is loaded with a unit point loads. So when you analyze this beam and draw the bending moment diagram, then the value of the moment at the point of that point loads is the ordinate of moment due to unit load. That's what we try to present on equation 17. So what it means that in equation 17, you draw the bending moment diagram based on the applied load given to you. Then remove those loads and in their place apply a unit point load. Then draw the bending moment diagram of that point load, and that's what you see here. When you multiply these two diagrams, you will arrive at deformation or displacement or deflection, as the case may be. So several cases have been arranged, solved, and their values presented on the table that follows. You can see the table. Above here are different shapes of bending moment diagrams. By the left side here is also different shapes of bending moment diagrams. Then within this place are the values of the diagram multiplication. When you multiply this moment diagram and this moment diagram, you will arrive at this, and so on and so forth. this is the continuation of that table. So what it needs is that you need to get this diagram multiplication table handy and use it and solve your problems of determining displacements. Yeah, we use the example to verify the authenticity of those formulas we gave in the table. In this example 1, we use two moment diagrams. It says determine the product of the area of M diagram and ordinates of M diagram. The diagrams are as shown here. Solution: the two diagrams shall be placed to align vertically. The centroid of M diagram shall be located. The ordinates y of the M bar shall be located to coincide with the centroid of M diagram. This is what we mean. This is the M diagram, this is the M bar diagram. They are now aligned vertically. Then we try to locate the centroid of the M diagram, and at that position we will get the ordinate of the M bar diagram called y. Here, similar triangular theorem can be employed to determine the value of y. You can see, applying the similar triangles, M bar over L equals y all over L over 3. If you solve out, you find out that y is equal to M bar over 3. The area of M diagram using normal half base times height is half ML. The deflection in this case is by multiplying the area of M diagram and that ordinate y. After doing that, you see is exactly the value we have in that table. This is another problem. The first one, we have two similar triangles, rectangle triangle. In this case, the M diagram is rectangle, whereas M bar diagram is triangle. Solution: the centroid of M diagram is at the midspan as L over 2. The ordinate of y, the ordinate y of the M bar shall be located to coincide with the centroid of the M diagram. So that ordinate is at the midspan also, y. Similar triangle theorem is also employed to find the value of y. After getting the value of y, you find the area of this rectangle. Then multiply the area of this rectangle with y. After we've done that, we got the equation, which is exactly as we have in the table. We have a third problem we are to solve. We still follow the same process. Find the area of the M diagram, locate the center of this diagram, and at that centroid you locate the ordinates of this particular M bar diagram. The ordinate of this M bar diagram should be at the position of the centroid of the M diagram. Then multiplying the area of the M diagram and that ordinate will give the displacement, which we so after doing that, the value we got tallied exactly with what you have on the table. This is number 4. This is a more practical example. Determine the deflection at 0.25 L and at 0.5 L from the left support of the simply supported beam with uniformly distributed load as you can see on the screen. Solution: the loaded beam will give parabolic M diagram. This load will be removed and a unit load applied at 0.25 L from the left support. This will give the first M bar diagram. This load will be removed and applied at 0.5 L from the left support. This will give the second M bar diagram. So this is the moment diagram, M diagram, for the loaded beam. So these loads will be removed, and at 0.25 L, that's from this point to this point, a unit point load will be applied and used to draw the embedded moment diagram, as you can see. Then that load will also be removed and applied at half of the beam, as half of the span of the beam, as at 0.5 L. So we now have three moment diagrams. The first one is the M diagram, the second and third one are the M bar diagrams. So what we need to do is to multiply the area of this parabola with the ordinates to get our displacement. So instead of doing the regular calculation, what you need to do is just to lift the formulas we have on the table. Just apply the formula and you get the displacement. It's simple and straight. But at this stage, we wouldn't want to apply the formula yet until we get the bending moment equations. By symmetry, the reactions at the two supports of the beam carrying uniform load Q are equal. That is, at support A and support B, the reactions are Q L over 2. The moment equation along the beam Mx is given as RAX minus QS squared over 2. That is QL over 2 times X minus QX squared over 2. If you factorize Q over 2 out, then in the bracket we have Lx minus X squared. The value of the maximum moment will occur at 0.5 L. So replacing X with 0.5 L will give us QL squared over 8 as the maximum bending moment for that parabola. The reaction at the support A of the beam carrying unit load, in this case located at 0.25 L distance away, is, as you see after solving out, is 3 over 4. The value of the moment at 0.25 L is RA times 0.5 L. That is 3 over 4 now times 0.5 L. That gave 3 L over 16. The reaction at support A of the beam carrying unit loads at 0.5 L distance away is, using the formula, 1 over 2. The value of the moment at that same position is RA times 0.5 L. That is 1 over 2 times 0.5 L, giving us L over 4. Now, to calculate the displacement as demanded, we go to the table and lift the formula. For the first one, we lifted the formula MO times MO bar into L squared plus AB all over 3L. After substituting the values of MO, in this case MO is QL L squared over 8, M bar is 3L over 16, then A is 0.25 L and B is 0.7 L. Substitute these values into this formula. After solving, we'll obtain that delta is 5QL raised to the power 4 over 539. That's the displacement at 0.25 L away from support A. The deflection at 0.5 L away from support A is also obtained from the table. Just go to the table, pick the formula. This is the formula. In this case, M is QL square over 8, M bar is L over 4, capital A is 0.5 L, capital B is 0.5 L. substitute these values into that displacement formula, solve out, and you will get that the displacement at 0.5 L away from spot A is 5 QL raised to the power 4 over 384. That is this. So you go to another example, example number 5. Determine the deflection under the point load and the center of the simply supported beam carrying point load P as shown. Solution. The loaded beam will give double arm triangle diagram. This load will be removed and a unit point load applied at So what I mean here is the loaded beam will give a double arm M diagram. This is due to the applied load. Then that load has to be removed and a unit point load introduced on that beam. It will still give us another diagram, in this case M bar diagram. So applying the unit load at the center will also give us another M bar diagram. Then multiplying the M diagram with the M bar diagram will give us the displacement we are looking for. For the case of external applied load P, as usual, we find the support reaction ROA. In this case, ROA gave us 0.6 P. We use it to apply, as we use it to determine the bending moment, that is at 0.4 L. ROA times 0.4 L will give us the bending moment value at that point. In the same way, the value of moment due to unit load at that same point is 0.24 L. The reaction of the beam at support A carrying unit load at 0.5 L away is half, 1/2. The value of the moment at that point is half times 0.5 L, that is moment times vertical distance. That gave us 0.25 L. We go to the table of moments diagram multiplication and leave the suitable equation for the displacement. That is the equation we have here, where M is 0.24 PL, M bar is 0.24 L, small letter A is 0.4 L, small letter B is 0.6 L, capital A is 0.4 L, and capital B is 0.6 L. Substituting these values into the displacement formula, which we obtained from the table, and using our calculator to calculate, we got displacement to be 12 PL raised to the power 3 over 625. So, substituting the values of M bar, A, L, A, capital B into that displacement equation, solving out gave us that final value for displacement, that is 13 PL raised to the power 3 over 661. This is example number 6. Calculate the support reaction of the beam shown using the method of consistent deformation method. It's a beam of 3 supports that is indeterminate to 1 degree. The middle support is redundant. This beam is indeterminate to 1 degree. Removing the redundant support will make the beam to be determinate. In this case, it's going to be a simply supported beam if you remove the center support. Draw the M diagram for the determinate beam, then remove the loads and apply a unit point load at the position of that another support, and draw the M bar diagram. Calculate delta B, calculate small d bb. The moment diagrams are the first diagram, which is parabola, is the M diagram. The second one, which is triangle, is M bar diagram. By symmetry, the reaction at the two supports of the beam carrying uniformly distributed loads for, that is, arrow A equals arrow B equals QL over 2, that is 6 times 8 over 2, that gave us 24 kilonewton. This is the reaction at support A and also the reaction at support B. The moment equation along the beam is arrow A times x minus qx square over 2, that is QL over 2 times x minus qs square over 2. Factorizing q over 2 out gave us q over 2 into lx minus x square. The value of the maximum moment will occur at s equals to 4 meters. That is, if you substitute in that formula, you get that maximum moment is 48 kilonewton meter. The reaction of the beam carrying the unit point load at 4 meters away from support A is, after calculation as presented here, gave us 0.5 kilonewton. The value of the moment due to this point load at 4 meters is, if you substitute, that is 0.5 times 4, will give us 2 kilonewton meter. So to calculate the displacement at 4 meters away, we go to the table and use the formula here for delta B. This is the formula we're going to use, where M is 48 kilonewton meter, M bar is minus 2 kilonewton meter, A is 4 meter and B is 4 meter. Substituting the value here, it will give us minus 320 kilonewton raised to power 2 and meter raised to power 3. I'm sorry, the unit load is just 1, so it has no units, it's just 1. So using it to calculate the bearing moment for M bar diagram, it's supposed not to give us 2 kilonewton meter but 2 meters. So I've done the correction. So the final value for delta B is minus 320 kilonewton meter raised to power 3, and not minus 320 kilonewton raised to power 2 meter raised to power 3. No. The answer is minus 320 kilonewton meter raised to power. The deflection, that's small d, substitute bb, that is due to point load applied at point B. You subtract from the table, get the formula. Where M bar is 2 meters, capital A is in small letter A, that is 4 meters, capital B is also in small letter A, 4 meters. Substituting the formula and calculating out, give us that small deflection as 32 over 3 meters power 3. I think we have come to the end of this lecture. You can see it's very interesting. We will not end here. Whatever we did here, we will carry over to our next class, where we shall do proper analysis, employing the technique we developed in this particular lecture notes. And at this point, I will say, till we meet again, I remain Chief Ous M. Ibadan, a leader of civil engineering, federal university of technology. Over. Thanks.